Volcanoes have always fascinated humanity with their power and unpredictability. These natural chimneys of the Earth are places where magma, gases, and ash rise toward the surface, creating spectacular eruptions that can transform landscapes within hours, days, or sometimes weeks. Volcanoes are both destroyers and creators. On one hand, their eruptions can annihilate entire cities, trigger pyroclastic flows, and flood rivers with lava. On the other, they form new islands, enrich soils with minerals, and shape the geographical map of our planet. At first glance, volcanoes may seem like menacing geological formations, yet their role in Earth's system is much deeper. They release gases that influence the climate, shape the hydrology of nearby regions, and their activity affects the lives of millions of people living in surrounding areas. Studying volcanoes allows us not only to understand geological processes, but also to predict hazards, plan settlements, and protect communities. In this chapter, we will look at both the most dramatic eruptions in history and the hidden processes that occur beneath the surface. From the movements of magma within volcanic chambers to the subtle signs that prepare the ground for an explosion. To understand volcanoes is to understand the dynamics of the planet, its forces of creation and destruction that operate constantly, sometimes subtly, and sometimes with brutally evident power. A volcano is, in fact, an incredibly complex geological system whose structure reaches deep beneath the Earth's surface and connects many processes that determine its strength, eruption character, and impact on the environment. At the very top of a volcano lies the crater, an opening through which gases, ash, and lava escape. The crater may take the form of a wide bowl or a narrow funnel, depending on the type of volcano and its eruptive history. Just below the crater is the volcanic conduit, a natural channel through which magma travels toward the surface. The conduit is not empty. Its walls are made of a mixture of solidified and partially molten magma, and inside there is extreme temperature and pressure that determine the dynamics of the eruption. Beneath the volcano lies the magma chamber, an enormous underground space filled with molten rock, gases, and minerals. It is here that pressure builds up, which at some point may eject hundreds of cubic meters of lava within minutes. The magma chamber connects with deeper layers of the Earth, where magma forms due to the melting of rocks under high temperature and pressure. These connections between the surface and the Earth's interior make every volcano unique. Even seemingly similar eruptions can vary in power and consequences depending on the composition of the magma, the amount of accumulated gases, and the structure of the conduit. Before magma reaches the surface, it contains dissolved gases, mainly carbon dioxide, water vapor, and hydrogen sulfide. It is the pressure of these gases that determines the violence of an eruption. The more gas, the more explosive the volcano's activity can be, depending on the magma's viscosity. A volcano can release fluid lava flows, forming gentle cones, or explode in a pyroclastic avalanche, throwing hot rocks and ash tens of kilometers away. Equally important are the secondary zones of a volcano: side fissures, fumaroles, and geothermal fields, which reveal the volcano's energy even when there is no active eruption. Fumaroles emit hot gases and steam, sometimes mixed with sulfur, while geothermal fields create hot springs and geysers. These elements show that a volcano is not just a moment of explosion, but a living system that constantly processes the Earth's energy, stores pressure, and interacts with its surroundings in subtle, invisible ways that are nonetheless crucial for life and the landscape around it. The most destructive volcanic eruptions in human history demonstrate how immense a force the Earth can unleash in a single moment, leaving behind dramatic consequences for both people and the environment. One of the most famous eruptions was that of Mount Tambora in Indonesia in the year 1805, considered the strongest eruption ever recorded. The explosion destroyed entire villages, ejecting billions of cubic meters of lava and ash into the atmosphere. The death toll is estimated at around 18,000 direct fatalities, with tens of thousands more dying from famine and disease caused by the destruction of crops. Volcanic ash and gases released into the atmosphere caused global cooling, known as the Year Without a Summer, which affected the lives of people and animals across the world. Another tragic example is the eruption of Krakatoa in Indonesia in the year 1896. The explosion was so powerful that the shock wave circled the globe several times, and the resulting tsunami wiped out the shores of the Sunda Islands, killing about 36,000 people. The sound of the eruption was heard thousands of kilometers away, and volcanic ash rose into the stratosphere, creating spectacular, colorful sunsets around the world for many months. Krakatoa showed that a volcano can become a global force, affecting not only the local area but also the planet's atmosphere and climate. The eruption of Mount Pelée on the island of Martinique in the year 1912 caused the deaths of about 30,000 people in the city of Saint-Pierre within minutes, as a massive cloud of hot gas and ash rushed down the slopes of the volcano. This event is an example of how extremely dangerous pyroclastic flows are. Violent, intensely hot streams of gas, ash, and rock that can travel at speeds of hundreds of kilometers per hour and destroy everything in their path in the blink of an eye. We should also not forget the eruption of the Eyjafjallajökull volcano in Iceland in the year 1992, which, although not a disaster with a large number of casualties, showed how volcanic activity can paralyze the modern world. Clouds of volcanic ash hovered over Europe for weeks, grounding thousands of flights and affecting the lives of millions of people. It served as a reminder that volcanic hazards have both historical and contemporary dimensions, and their effects can be global even in the 21st century. Analyzing these catastrophes, it becomes clear that volcanoes operate on many levels. They destroy human settlements, reshape landscapes, influence the climate, and sometimes affect the lives of entire continents. History shows that ignoring the power of volcanoes can have tragic consequences, but it also provides valuable knowledge about the geological mechanisms that shape our planet. Every eruption is a unique spectacle of nature's forces, in which energy accumulated over millions of years is released in a single moment, leaving a lasting mark on the history and geology of the Earth. Volcanoes are among the most spectacular and dangerous geological formations on our planet, yet at the same time, they serve as the fundamental architects of the Earth. Since Precambrian times, their activity has shaped the planet's surface, ejecting lava, ash, and volcanic gases, forming new crust, building mountains, islands, and atolls, while simultaneously bringing dramatic changes to the atmosphere and oceans. Volcanic islands such as today's Pacific archipelagos, Hawaii, the Galapagos Islands, Fiji, or Tonga, were created by long-term volcanic activity, and their soils, rich in minerals, provided conditions for plant and animal life, and later enabled human settlement. Volcanic eruptions have shaped the geological history of the planet in ways still readable today in rocks, layers of ash, and the structures of islands. The most powerful eruptions have been capable of transforming continental landscapes within days, altering rivers and lakes, and even influencing the global climate, triggering periods of cooling or local droughts. History records eruptions that nearly halted the progress of civilization, such as the eruption of Mount Tambora in 1814, which caused the so-called Year Without a Summer in Europe, bringing crop failures, famine, and mass migrations. Yet volcanoes did not only destroy, they left behind fertile volcanic soils, which allowed people to cultivate crops and build settlements, while volcanic islands became havens of life even in the most remote parts of the ocean. To this day, volcanoes continue to shape ecosystems and human life. In Hawaii, Indonesia, the Philippines, and the Canary Islands, volcanic soils support agriculture, and hot springs and geothermal energy are used for power generation and recreation. Volcanoes also form atolls, ring-shaped coral islands surrounding lagoons built upon the foundations of ancient volcanic islands. These extraordinary biological structures provide shelter for hundreds of species of fish, birds, and plants, and for humans they serve as sources of fishing, tourism, and culture. This shows that volcanoes, though destructive, in the long term, become the foundation of life and survival. The influence of volcanoes on evolution and species migration cannot be overstated. Lava and ash created new habitats, altered river courses, formed lakes and new coastlines, while climate changes triggered by eruptions forced adaptation and natural selection. Even humans had to learn to coexist with these forces. Settling near volcanoes was risky, but also attractive because of fertile soil, access to resources, and strategic location. Volcanic processes are not confined to the past. Active volcanoes still reshape the Earth in ways that are difficult to imagine. Every eruption, whether a quiet stream of lava or a powerful Plinian explosion, transforms the landscape, affects the atmosphere and oceans, and forces ecosystems to adapt. Volcanoes also influence the climate, releasing vast amounts of dust, sulfur dioxide, and other gases into the atmosphere, which can temporarily cool the Earth's surface or alter rainfall patterns. Moving from volcanoes to glaciers, one can easily notice the contrast between the forces of fire and ice. Both elements sculpt the Earth's surface, creating new forms of life and influencing the climate. While volcanoes build islands and mountains, glaciers carve valleys, transport rock material, and form lakes. These are two opposing yet complementary mechanisms that, throughout Earth's history, have co-created the planet's landscape, climate, and life. Submarine volcanoes, though hidden beneath the surface of the oceans, are among the most active and fascinating structures on our planet. While most people imagine volcanoes as spectacular eruptions on land, over 80% of Earth's volcanic activity actually takes place underwater. These extraordinary formations occur in places where the Earth's crust is thinner or where tectonic plates separate or collide. As lava emerges, it forms underwater mountains that can eventually rise above the surface, creating volcanic islands or chains of atolls. Submarine volcanoes not only shape the seafloor but also have an immense impact on marine life. Hot mineral vents from their fissures provide nutrients that attract plankton, fish, crustaceans, and entire ecosystems that thrive in extreme conditions. Around these hydrothermal vents, scientists find unique species adapted to survive in temperatures lethal to most organisms and in waters saturated with hydrogen sulfide and metals. Thanks to these living laboratories, the underwater world remains extraordinarily diverse and full of remarkable adaptations. As lava flows and cools, it forms new seafloor, gradually elevating it until part of it emerges above the ocean's surface. This is how Hawaii, Iceland, and the Galapagos Islands were formed, along with hundreds of smaller islands that for centuries served as navigation points, sources of mineral resources, and sites of human settlement. Some of these islands developed unique ecosystems, found nowhere else on Earth. Submarine volcanoes are, therefore, not only a geological phenomenon, but also a foundation of oceanic life and a catalyst for the creation of new lands. Through them, the Earth continues to change, and life in its deepest realms finds new opportunities to evolve. When an underwater volcano grows and rises above the surface of the ocean, a new volcanic island is born. A process that may take hundreds of thousands of years, though it can sometimes accelerate through a series of powerful eruptions. At first, the islands are raw and almost lifeless, consisting mainly of solidified lava, ash, and volcanic rock. Over time, however, wind, rain, and chemical processes begin to transform this hard surface into a more hospitable environment. Volcanic dust, rich in minerals, becomes the foundation for the first forms of life: algae, lichens, and mosses. These organisms not only colonize the surface but gradually break down the rock, creating the first layer of soil, which eventually allows flowering plants and shrubs to settle on the new land. Volcanic islands are often dynamic, constantly changing through both eruptions and the action of waves and wind. Over time, they can develop into complex ecosystems that attract birds, insects, and eventually mammals and other animals. In some regions, such as the Pacific, these islands form entire archipelagos that serve as habitats for unique species of plants and animals found nowhere else on Earth. Thanks to geographic isolation, Specific flora and fauna evolve here, often developing characteristics that could not emerge under any other conditions. Some volcanic islands eventually transform into atolls. An atoll forms when the volcanic core gradually subsides or erodes, while coral reefs develop along its edges. These reefs not only protect the island from waves and erosion, but also create new aquatic ecosystems teeming with life, from fish and crustaceans to unique species of coral and marine plants. The atoll becomes a microcosm of life, where both marine organisms and seabirds find their place within a complex web of interdependence. Underwater volcanoes, volcanic islands, and atolls demonstrate how geology and biological life are inseparably connected. Every eruption, every new outflow of lava is an opportunity for life to expand, while erosion and soil formation processes allow entire ecosystems to arise from nothing. As a result, our planet is constantly evolving. The seas and oceans, which seem stable and unchanging, are in fact a stage for the continuous birth of new lands and habitats for countless life forms. For ages, volcanoes have not only shaped the Earth's surface, but also had a tremendous impact on the planet's climate and life. Every eruption is not only a torrent of lava or a cloud of ash, it is an event that shakes the atmosphere and oceans, sometimes on a global scale. Volcanic gases such as sulfur dioxide, nitrogen oxides, and water vapor released during eruptions rise high into the atmosphere and can form vast layers of aerosols that reflect solar radiation back into space. The result is that for months, and sometimes even years, the Earth's average temperatures can drop, causing global cooling. Historical examples show that large volcanic eruptions could lead to serious climatic changes, famine, and social upheavals. For instance, the eruption of Mount Tambora in 1813 caused the so-called year without a summer in Europe and North America, when crops failed and temperatures dropped so drastically that harvests almost completely vanished. The impact of volcanoes on climate is not limited to cooling. Some eruptions cause localized warming, especially in underwater volcanic regions, where the ocean water heats up and affects marine currents. Moreover, emissions of carbon dioxide and other greenhouse gases, though minor in the short term compared to human activity, have historically contributed to long-term climatic shifts, including warm epochs and mass extinction events. Volcanoes can also alter atmospheric circulation, creating new wind and rainfall patterns, and eruptions in tropical regions often lead to changes in monsoon cycles and rainy seasons. Interestingly, volcanic ash is not always destructive to life. On a local scale, it provides soils and waters with rich minerals, helping ecosystems regenerate after disasters. On a global scale, however, each powerful eruption reminds us how thin the boundary is between a stable climate and the violent transformations that in the past have reshaped civilizations and entire geographical landscapes. Observations of modern eruptions, such as Eyjafjallajökull in Iceland or Pinatubo in the Philippines, allow scientists to better understand the complex relationships between geology and the atmosphere and to predict the effects of future events. Geothermal and volcanic energy represent one of the most fascinating applications of the Earth's natural processes. Beneath the planet's surface lie immense amounts of heat, remnants of its formation, as well as the result of radioactive decay deep within. Volcanoes and geothermally active regions are, in this sense, windows into the Earth's interior, places where this energy becomes accessible to humans. For centuries, people have used hot springs for bathing, heating, and healing. But only in the 20th century did scientists begin exploring how this heat could be transformed into electricity. Volcanic regions such as Iceland, Italy, Japan, and the Philippines have become natural laboratories for geothermal development. In these places, the Earth's crust is thinner, and magma chambers lie relatively close to the surface. Water heated by hot subterranean rock forms steam, which can drive turbines and generate power. Unlike fossil fuels, geothermal energy is practically renewable. The heat continuously flows from within the Earth, and well-managed sources can provide energy for decades or even centuries. One of the best-known examples is Iceland, where nearly 70% of electricity comes from geothermal sources, and hot springs heat homes, hospitals, schools, and hotels. In Tuscany, Italy, the world's first geothermal power plant was built in the late 19th century, showing that humanity has long been able to harness the forces of the earth. In Asia, particularly in Japan and the Philippines, volcanoes and thermal zones form the backbone of local energy production, as well as tourism and the spa industry. Geothermal energy is not only clean but also stable. Unlike wind or solar power, which depend on weather conditions, geothermal sources deliver energy almost continuously. However, their exploitation requires knowledge and caution. Poor management can lower thermal water levels, cause ground erosion, or even trigger seismic activity. That is why modern geothermal plants are equipped with monitoring and pressure regulation systems that balance energy extraction with the natural flow of heat. Interestingly, geothermal energy and volcanoes still hold many mysteries. Scientists are exploring the potential of deep geothermal energy, reaching several kilometers beneath the crust, where temperatures rise to several hundred degrees. Although the technology is costly and demanding, its potential is enormous. Billions of people could benefit from a virtually limitless energy source. Volcanic energy not only transforms how we think about electricity and heating, but also reminds us that the Earth is a living, dynamic organism still offering opportunities for human cooperation with nature. Geothermal and volcanic energy represent a story of discovery, innovation, and cautious collaboration with the powerful forces of our planet. It is energy that beats within the heart of the Earth, quiet, stable, and unceasing, ready to serve humanity if only we learn to respect and use it wisely. For centuries, volcanoes have both fascinated and terrified humankind. But only in the modern scientific era have we come to understand that their destructive power can be observed, analyzed, and sometimes even predicted. Volcano monitoring is a field where technology and nature meet in a remarkable way. Scientists not only observe the surface but listen to the Earth's interior and interpret its subtle signals. Every volcano is like a living organism sending faint messages, vibrations, temperature changes, gas emissions, or ground deformations that may herald an eruption. The foundation of eruption prediction lies in seismometers, extremely sensitive instruments that record the Earth's vibrations. When magma begins to rise within a volcanic chamber, it causes microquakes that are almost imperceptible to humans, but serve as the first warning signs for scientists. Every tremor, its frequency and intensity, is carefully analyzed, and patterns are compared with the history of previous eruptions. Such data allow researchers to determine whether a volcano is awakening slowly or preparing for a sudden, violent eruption. Volcanoes are among the most dynamic structures on our planet, and their existence is inseparably tied to the movement of magma deep within the Earth. The question of whether a volcano can truly die forever seems simple, yet it is, in fact, quite complex. It requires an understanding of the forces that drive eruptions and the geological processes that lead to a volcano's death. In general, volcanoes are classified as active, dormant, or extinct. An active volcano is capable of erupting at any moment. A dormant one may remain silent for hundreds or even thousands of years before suddenly awakening. And an extinct volcano is one that has lost connection with its magma source so deeply that an eruption becomes almost impossible. The process of a volcano's extinction usually takes tens of thousands, or even millions, of years. As tectonic movements and the cooling of magma gradually cut off the flow of molten rock, the volcano begins to lose its vigor. Its crater slowly erodes under the forces of wind, rain, and glaciers, and the once prominent cone becomes little more than a soft outline on the landscape. Yet even after thousands of years, when a volcano appears lifeless, small pockets of magma can still linger deep below the surface, and under the right conditions, they may reignite minor eruptions. That is why the term extinct volcano is always relative rather than absolute. Some volcanoes do indeed die completely, but this typically happens when their magmatic systems are permanently severed by shifts in tectonic plates, or when the remaining magma cools and solidifies entirely. Good examples of truly ancient extinct volcanoes can be found in the Rocky Mountains or the Sudetes, where today only weathered remnants of ancient cones remain. silent witnesses of a fiery past long gone. In contrast, regions like Hawaii or Iceland tell a different story. Beneath their surfaces, magma is still on the move. Even if a volcano rests quietly for centuries, it doesn't necessarily mean its fire has gone out forever. Volcanic life can also be interrupted by tectonic change. When the movement of plates or a decrease in magmatic activity cuts off the flow of molten rock, the volcano effectively dies. Yet in geological time, this death is rarely final. New fissures can open nearby, giving birth to fresh volcanic cones. In this way, the volcanic life of Earth is not a series of isolated events, but a continuous web of processes that has persisted for millions of years. Each volcano, whether silent or raging, plays its part in the planet's eternal rhythm, a reminder that even what seems dead may still carry the pulse of creation deep within. One could say that a volcano can go out in the sense of losing its activity and eroding into the landscape, but it can never be completely ruled out that, deep within the Earth's crust, some remnant of magma remains, waiting for the right conditions to trigger a minor eruption. Even a volcano that appears lifeless stands as a monument to the constant movement of energy inside our planet, a reminder that Earth itself is alive, its hidden interior still shaping the surface, the landscapes, and the history of life that unfolds upon it. Now imagine the eruption of a supervolcano, an event so vast that it defies the human imagination. The largest volcanoes on Earth, such as Yellowstone, Toba in Indonesia, or Campi Flegrei in Italy, dwarf typical volcanic cones in scale and power. Their eruptions would not merely devastate local surroundings. They hold the potential to alter the climate, reshape continents, and change the very course of human history. If Yellowstone were to erupt today, the beginning of the catastrophe would be both spectacular and immediate. The immense pressure within its magma chamber would expel hundreds of cubic miles of lava, ash, and volcanic gases within hours. The ash cloud would rise into the stratosphere, spreading across the entire northern hemisphere. Sulfur and volcanic dust suspended in the atmosphere would reflect sunlight back into space, causing a rapid drop in global temperatures, the so-called volcanic winter. Within months, average temperatures around the world could fall by several degrees, triggering a short but catastrophic collapse of agriculture and widespread famine. The devastation near the crater would be beyond comprehension. Lava flows, pyroclastic surges, and searing avalanches of ash and gas would annihilate everything within hundreds of miles. Ash would blanket tens of thousands of square miles, poisoning rivers, lakes, and soil, rendering life nearly impossible for years. Toxic clouds of sulfur dioxide and carbon dioxide would produce acid rain, corroding infrastructure and altering the chemical balance of ecosystems. The global consequences would be equally dramatic. Ash suspended in the stratosphere could block sunlight for months or even years, plunging the planet into darkness and cold. Crop yields would collapse across nearly every continent, leading to food shortages and social unrest. Changes in temperature and rainfall would disrupt animal migrations and force ecosystems, both terrestrial and marine, to adapt or perish under sudden environmental stress. The impact on humanity would be staggering. No one near the eruption zone would survive, but its indirect effects could touch billions of people worldwide. Civilization itself would be forced to adapt. History tells us that past supervolcanoes have coincided with mass extinctions and global climate shifts. The eruption of Toba, roughly 70,000 years ago, is believed to have reduced the human population to only a few thousand individuals, a bottleneck that nearly erased our species. In such a scenario, survival would depend on adaptation. People would have to migrate away from regions buried in ash, seek refuge underground, stockpile food and water, and form resilient communities capable of enduring cold and darkness. Solar power would fail, forcing reliance on other sources, firewood, geothermal energy, or fossil fuels where available. Food would need to come from hunting, fishing, or underground agriculture. Crops grown in greenhouses and tunnels shielded from the choking ash. Animals, too, would be forced to migrate, reshaping ecosystems on a global scale. Birds and mammals would seek habitable zones, while marine life would struggle to survive in colder, darker oceans. Regions covered in volcanic ash would remain barren for decades, their scarred landscapes slowly healing under the forces of wind, rain, and time. Fortunately, the probability of a Yellowstone eruption in the near future is extremely low. Scientists continuously monitor ground deformation, gas emissions, and seismic activity to provide early warnings. Yet the mere existence of such giants reminds us of the immense, unpredictable power of our planet. Supervolcanoes stand as a humbling testament to the fact that Earth is not a static world, and that despite our technological progress, human civilization still lives at the mercy of forces far greater than itself.